So I wrote down the wave equation up here, sort of disembodied from this. I told you that this sort of represents this, propagation outward of either energy or disturbances, just like pebbles dropped into a pond. Okay, but can we get a handle on the derivation of this? Okay, and one place that people often start is with the example of a vibrating string. Okay, so the idea here, okay, is that we want to take a plucked string, okay, and sort of map coordinates in the right way so that we can get the propagation of energy or displacement along the string in terms of the wave equation. We're going to have to do some approximations, okay? But the idea is that we're mostly going to be guided by the physics of tension and momentum. And at the end of the day, just the physics should give us this PD that comes out, okay? So let's start with just writing down some coordinate frame, X and Y. And let's say that we have a string that's stretched from 0 to 1 initially, okay? And that we pluck the string so that it's displaced from 0 to some length L now, okay? And our coordinate now is going to be how much or what the position is of the string in two-dimensional space, okay, relative to where it would be at equilibrium. So this X here is our sort of original coordinate, but remember, because it's stretched, okay, we can stretch out this unit interval that was originally from 0 to 1 up to 0 to L now, okay? And so that's going to be a vector in two-dimensional space, this R, okay? You're at any particular point, you're going to have some tangent to that that's given by Rx, okay? And our coordinate system now in the moved string is R1 and R2, okay? So the idea is that we have a 1D string and it's deformed into 2D, okay? R1 and R2 are going to be equal to this vector function R of xt, okay? And we have some tangent to the string that's given by Rx xt, okay? Okay. So now a bit about the assumptions that we'll use. First of all, you only are going to have motion in R2, okay? And so that's given by this description here of R. The other thing is that the string tension is very large, okay? So this string is really well stretched out here. And so what that allows us to do is that we can neglect gravity, okay? If this string were not stretched very well here, it might hang down and we would get some effects of gravity or the mass on the string. okay? There's also going to be no resistance to the bending, okay? So no force resistance, okay? And also we're gonna have a uniform cross-section area A. So this is like, if you looked at this, the inside of the string, it's just a, it's a chord whose cross-section is like circular. And then if you, look at a portion of the string, it has some density rho that tells us how mass is distributed along the string, okay? And the way that we can get the wave equation here is that we'll derive it using conservation of momentum, okay? And so the only force on the string is due to tension, okay? T hat, which is tangential to the string, okay? And that can be computed with Newton's laws, okay? So in these new coordinates here, right, our x, we'll say, can go from 0 to L, okay? The important relationships that we're going to have are going to arise from the connection between the stress and strain of elastic material, okay? So a few more preliminaries then is that if we take Newton's second law, it's force equals mass times acceleration. Here, what's our acceleration? Well, that's going to be how fast the string moves, okay? Our mass is going to be rho A delta x, okay? What's the force then that's acting on the string to produce this acceleration of the mass, okay? Well, it's the force that's occurring in the tangential direction due to the how the string's getting stretched out, how tense the string is. And so our force is going to be A times the tangential tension here, amplitude multiplied by that tangential direction, okay? So for any interval, A to B, we can basically integrate rho A r t t x t dx, and this is equal to A t hat rx divided by the magnitude of rx evaluated between A and B, okay? So that's it. So this is mass times acceleration, because we have to integrate density to get mass, is equal to the force that's producing that, okay? And so, so if we use the fundamental theorem of calculus, we can just rewrite this as A t hat Rx differentiated with respect to x and then integrated again. So at the end of the day, what we have is rho A RTT is equal to A T hat Rx divided by Rx differentiated with respect to X. So just by applying Newton's law, okay, we've gotten something that sort of is starting to look like what we want. We have a second derivative with respect to time. That comes from, the acceleration term. And the force just comes from, well, our expression for the tensile force, okay, and then taking a spatial derivative of that, okay? So we need a few more steps to sort of get us where we need to be. I think I'll just talk for a few more minutes and then I'll have to conclude, okay? But one constitutive assumption is that the tension that's acting on the string, okay, should be some function of the magnitude of the tangent, like how deformed it is. So this, the deformation basically of this string is going to be encapsulated by this tangent, okay? So the more, the more it's sort of stretched out, the more tension that's going to create in the string, okay? So this should be some function of the magnitude of that tangent. So this only really depends on the strain. The tension should only depend on the strain, okay? The magnitude of Rx. We're also called the deformation gradient, okay? And in general, okay, the stress-strain relationship for elastic material, okay, has the following sequence of events, okay? If you apply force to some material, okay, then it undergoes strain, okay? The strain, in turn, okay, causes the material to resist and this is the stress in response to that strain, to return to equilibrium, okay? So if you cause stress to a elastic material, it will respond with strain, okay? This is the resisting force. Essentially, you have force, okay, which creates strain, and then the result is stress, okay? So our string equations, right? I'm going to have to wrap up here shortly. Our string equations now tell us that RTT is going to be, so if I divide through here, right, by this, then I get RTT is equal to T of Rx, the magnitude of that, Rx divided by Rx, differentiated with respect to X. okay? And that's defined on x goes from 0 to L, t greater than 0, okay? So what have I done with A? Well, the A's cancel out, and the rho just is scaled into this function for the tension as it's affected by the deformation gradient here. Okay, how the tension depends on the strain. Okay, so what you would imagine is that probably the next thing we're going to have to do is maybe some sort of Taylor expansion, which is what we do. We show that that Taylor expansion is legal as long as, you know, the deformation is not too large. And as a result, we can get a nice linear equation, which ends up being our wave equation, okay? But for now, we're gonna have to call it a day, and we'll finish this up on Monday. You're gonna also ask me questions about this on Friday if you want, if you get a chance to look it over before then. Okay, so thanks for that. And